Okay, I'm going to begin section 3.2 now. In section 3.2, we're going to talk about what's called the product and the quotient rules. The product rule and the quotient rule are super important. We're going to use both of these all over the place for every single chapter. Okay, so I would memorize these two formulas. Like I said, we'll be using them a lot. We'll start with the product rule. So suppose that, now in the last section, I had mentioned that the derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference in the derivatives. Now, what about if you have a product or a quotient? Well, the derivative of a product is not the product of the derivatives. The derivative of a quotient is not the quotient of the derivatives. So don't make that mistake. Okay, the product rule says that the derivative of a product, f of x times g of x, is where you take the first times the derivative of the second plus the second times the derivative of the first. Okay, memorize that. We'll look at some examples here in just a moment, but let's take a look at a proof of where this is coming from. So I'm going to compute the derivative with respect to x of f of x times g of x. Well, I'm going to use the limit definition. Again, all the differentiation rules come from the limit definitions. So I need to find the limit as h approaches 0 of the difference quotient. Okay, here would be the difference quotient for the function that I want to differentiate here. And now with this, there's a kind of a creative move here that will have this work out. So in the numerator, let me subtract f of x plus h times g of x, and then add f of x plus h times g of x. Okay, I'm going to put that right in the middle of these two terms here. Now there's no harm with doing that because these two terms are opposites, so it's like I'm just adding 0 in the numerator to what I've already got. Okay, now in the numerator, I'm going to, actually the next thing I'm going to do is I'm going to go ahead and split this into two fractions. Okay, now with the first fraction, f of x plus h would be in common to those two terms in the numerator. Let's go ahead and factor that out. The leftover then on that first fraction would be g of x plus h minus g of x all over h. Plus, okay, now in this other fraction, g of x is in common to these two terms. Let's go ahead and factor that out. And the leftover on this second fraction here would be f of x plus h minus f of x all over h. Okay, now I can use my limit laws. The limit of a product is the product of the limits. The limit of a sum is the sum of the limits. So I can go ahead and split this into 4 limits. And, okay, the limit as h approaches 0 of f of x plus h, well, that'd be f of x. I can make a direct substitution there. The limit as h approaches 0 of g of x plus h minus g of x all over h, that'd be, by definition, how we define g prime of x. Okay, plus the limit as h approaches 0 of g of x, well, g of x is a constant, right? This limit is in terms of h. I have nothing in terms of h here inside, so limit of a constant is always the constant. You're going to get g of x. Limit as h approaches 0 of f of x plus h minus f of x all over h. That would be, by definition, how we define f prime of x. Okay, but that's where I had to get to, right? We had to show that when we differentiate with respect to x, f of x times g of x, we get f of x times g prime of x plus g of x times f prime of x. Or the first is always the first times the derivative of the second plus the second times the derivative of the first. All right, so let's take a look at some examples now where we're using the product rule. Here's an example. Suppose that we want to differentiate h of x. So h of x is a product, right? I'm multiplying these two expressions, and so I can use the product rule. Well, I'm going to want the first times the derivative of the second plus the second times the derivative of the first. Okay, I'm using the d dx notation here to indicate that I'm going to differentiate this expression. Okay. Well, let me go ahead and differentiate these two expressions. So the derivative of 5 plus 4x, that'd be 4, right? Derivative of 5 is 0. And the derivative of 3x minus 2x squared, that'd be 3 minus 4x. Okay, and of course, remove the d dx notation. You've now calculated the derivative of these two things here. And now at this point, it just becomes a process in simplifying as far as you can go. Okay, let's distribute the 4. We'll FOIL this out, and then we'll collect our like terms. So let's see, 3x times 4 is 12x, and then it's going to be a minus 8x squared. When I FOIL this out, I'm looking at 15 minus 16, minus 20x plus 12x, and then minus 16x squared. Okay, these two terms are like terms. You're going to have negative 24x squared, and then 12x plus 12x is 24x, minus 20x is 4x, and then a plus 15 at the end. Okay, and that would be as simplified as we can get it. Now, a couple things. So I have emphasized in the last, in the previous video there, make sure that you're simplifying. Okay, the book will really drill that in here over the next several sections. They're going to want you to simplify as far as you can go. Like anything else that you do in math, simplify as far as you can go. Now, they want to make that kind of a habit because we're going to be doing lots of simplifying here later on once we get to the application stuff. Okay, so they just kind of want to make it a habit, from the start, that you're going to not only would you take the derivative, you're going to then simplify as far as you can go. All right. Now, another way that I could have done this problem is I suppose that I could have simplified the original function. I could have FOILed this out and then differentiated each term individually. I would have still got the same answer. I don't think that the work would have been any longer or shorter if I would have done it like that. It'd be just another way to look at the problem. Okay, here's another example. Okay, suppose that we have the function r of t. R of t is a product, so that suggests that I would want to consider using the product rule. Okay, now sometimes if you have a product, you don't have to use the product rule, like you're not forced to do that, but sometimes you will have to use the product rule. Like if I were to begin by simplifying this, like FOILing it out, I would need to use the product rule on the last term. That would be my only option. Okay, so I would say that no matter what I do here, if I simplify to start or simplify later when I calculate the derivative, either way I'm going to have to use the product rule. Why don't we just start with the product rule then? Okay, so it's the first times the derivative of the second plus the second times the derivative of the first. Okay, and I've indicated the derivative notation. When you guys are computing, you don't need to use the derivative notation if you've already just calculated the derivative. Okay, so I would recommend, just to save a line, just go right to the line where you've calculated the derivative. Okay, and of course, if you are using the notation, make sure that you're using it correctly. Right. So the derivative of 3 is 0. The derivative of negative t to the 1/2 is how I'd want to look at that. So then I can use the power rule. That would be negative 1/2 t to the negative 1/2. Okay, plus, I got the second there, I'm leaving that alone, times the derivative of the first. Derivative of t is 1. Derivative of e to the t is itself e to the t. All right, and of course remove the d dt notation. You've already calculated the derivative now. And so now I'd want to simplify. Okay, let me distribute this term into these two, and I'll have to FOIL out this part. So we're going to have negative 1/2 t to the negative 1/2 times t would be negative 1/2 times t to the 1/2, or t to the 1/2 would be the square root of t. And then minus 1/2 e to the t times t to the negative 1/2, well, that'd be the same as 1 over t to the 1/2, or 1 over the square root of t if you're using radical notation. And when I FOIL this part out, okay, 3 times 1 is 3. The outer terms would be 3 e to the t, and then minus root t in the middle, and then minus e to the t times root t at the end. Okay, now I guess this term and this term are like terms. That's my only like terms, so I'll go ahead and combine those two together to get the negative 3 halves times the square root of t. Everything else would stay just as you see it there. Okay, so go ahead and circle, that'd be the answer. Here's the quotient rule. So the derivative of a quotient, f of x divided by g of x, is this rule here. Okay, you're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. Okay, and of course g of x can't be 0. Memorize that. Okay, again, the product rule and the quotient rule are going to be seen all over the place, and eventually they're going to want you to get very, very good at this stuff. Okay, they're going to want you to calculate the derivative like it's nobody's business, right? So make sure that you memorize, make sure that you practice. Okay, it's super important. Let's take a look at the proof of the quotient rule. So the derivative of f of x over g of x. Here's what I need to get to. Well, let me start with the limit definition. I need the limit as h approaches 0 of the difference quotient. Okay, so here's the difference quotient for this function. And the next thing I'm going to do, so in the numerator, let me go ahead and cross multiply so that I get a single fraction here. It's going to be g of x times f of x plus h, and then minus f of x times g of x plus h, all over g of x plus h times g of x, all over h over 1. Now the h over 1, the fact that you're dividing by a fraction, that can be flipped. So you'd be multiplying this guy here by 1 over h. So let me go ahead and just stick an h in the denominator there by g of x times g of x plus h. Okay. Now, of course, I can't plug in 0 yet, right? There's a move that happens to make this work out, kind of like what you saw in the proof of the product rule. So in the numerator here, I'm going to subtract f of x times g of x, and then to offset that number, since I just can't add a number wherever I please, I'm going to add f of x times g of x. Okay, that way it's like I'm adding 0 here with these two terms and I haven't changed anything. In the denominator, okay, if I have h times g of x plus h, I can rewrite this as a division by g of x times g of x plus h over 1, right? Because I'm dividing by a fraction, I'd flip the denominator and multiply. So when you take this guy here, all in the numerator, and multiply by 1 over g of x times g of x plus h, you get the line before. Now, keep in mind where I'm trying to get to. I'm trying to get to this formula here in the calculation, right? So there's a lot of working with fractions going on. That's okay, you know, no biggie. So, but in the numerator, this part, I'm going to go ahead and split this single fraction into 2 fractions. Okay, and then I'm also going to split the limit into what would be 3 limits. I got 2 fractions in the numerator and then this term down under. Okay, let me go ahead and do that. Now with the first fraction, g of x is in common to those 2 terms. I can factor that out, and the leftover then would be f of x plus h minus f of x all over h. Minus, with the second term, f of x is in common, and I can go ahead and factor that out. The leftover fraction then would be g of x plus h minus, since I'd be factoring out an f of x here, and so it would be a minus g of x all over h. Okay, and The denominator I'll just keep as is. So the next thing that you're going to do once you split this is you're going to go to the answer. Okay. Limit of a constant is always the constant, so you're going to have g of x times the limit as h approaches 0 of f of x plus h minus f of x all over h. That'd be, by definition, f prime of x. And then minus the limit of a constant is always the constant, f of x, times the limit as h approaches 0 of g of x plus h minus g of x all over h. That would be, by definition, how we define g prime of x. And then in the denominator, okay, limit of a product is the product of the limits, right? And limit of a constant is always the constant, so you're going to have g of x times the limit as h approaches 0 of g of x plus h. You can plug h directly into that, and you get g of x. G of x times g of x is g of x squared. And yeah, so that's what I had to get to, right? That's the formula that we see. So we're looking at the bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. And let's take a look at some examples now where we're using that. Here's one example. Okay, I've got a quotient, so I'd want to consider using the quotient rule. Y prime would be where I take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. Okay, let's go ahead and differentiate these two expressions. The derivative of x cubed is 3x squared. The derivative of 4x is 4. Derivative of constant is always 0. Over here, the derivative of 7x is 7. Derivative of constant is 0. Okay, now at this point, I would just simplify as far as possible. So I would need to FOIL this part out, distribute the 7, and that's what I've done in the next line here. And okay, it looks like we're going to have 28x minus 28x, those terms cancel. And then I can combine my other like terms. 21x cubed minus 7x cubed is 14x cubed. Be a plus 9x squared. Again, these terms have canceled. And then 12 plus 14 is 26. Okay, now usually when you work with the quotient rule, usually you're going to keep the denominator in a factored form, like how you see. You know, you could, like in this problem, you could FOIL out 7x plus 3 times 7x plus 3. There's no problem with that. It's just usually we don't need to do that for any reason, okay? Although you can if you want, but I would say try to leave it in a factored form, because many times later on you're going to have something that will cancel with part of the denominator. Okay, we'll see that on occasion, so you know it's helpful to just leave it in a factored form in order to see that cancellation occur. Let's take a look at another example. Okay, so how about y equals 3 minus 1 over x all over 1 minus 2x. Okay, now this would be a quotient rule situation. But if I were to use the quotient rule right away in this form here, I would have a quotient rule within a quotient rule. Okay, since I would have to differentiate 1 over x, which I could actually probably rewrite that as a x to the negative 1 and treat that as a power rule. Okay, but to avoid a quotient rule within a quotient rule, I'd say why don't we go ahead and simplify first, and then that way we'd only need to use the quotient rule one time. So let's do that. And, 3 minus 1 over x, that'd be 3x minus 1 all over x. I'm dividing by 1 minus 2x all over 1, right? So flip the denominator and multiply. 3x minus 1 over x times 1 over 1 minus 2x would be 3x minus 1 all over x minus 2x squared. Okay, so now let's use the quotient rule on this. I've got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. Okay, and I'm using Leibniz notation, that's fine. Y prime and dy dx, f prime of x, they all mean the same thing, right? So then I'm going to take the derivative of these two things here. Derivative of 3x minus 1 is 3. The derivative of x squared minus 2x, the derivative of x minus 2x squared would be 1 minus 4x. Okay, and from what I was saying earlier, you know, I would encourage you maybe to just kind of go right to this line and skip the derivative notation, like you don't need to tell me what you're differentiating. Go ahead and just take a derivative, you know. So now we're at this point, and I want to simplify, distribute the 3, FOIL this part out. Okay, and here's what I got. Now I'm subtracting this whole thing, right? So I'd want parentheses around this, these 3 terms after I FOIL. And combine your like terms. Okay, negative 6x squared plus 12x squared is 6x squared. 3x minus 7x is negative 4x, and then I'm adding 1 there at the end. And again, you can just leave the denominator in a factored form. That'd be great. There's no reason to FOIL this part out, although you could if you wanted. All right. Be sure to look at the problems in this section. I feel like this is a very important section that, you know, if you struggle with things here, that's going to be a kind of a big problem for several things later. The homework is on page 188, and yeah, be sure to look at the odd numbered problems for me that are listed there.